Now, another thing I mentioned before is what about infinity? How do we define that? What's the intuitive idea or definition behind a limit in that case? And with infinity, it's a little different. Let's go ahead and just look at an example. It says, let f be a function defined on both sides of a, except possibly at a itself. It says the limit as x approaches a of f of x equals infinity means that the value of f of x can be made arbitrarily large, aka infinite, by taking x sufficiently close to a. And again, this is just sort of a way of saying that as x gets near a, the value of f of x will get as big as we want. It will be technically equals infinity. It's not like an equation. You can't have infinity in an equation, and nothing can actually equal something infinite, but a limit can be equal to infinite. It's just a notational way of saying that this limit is unlimited. Really, there is no limit is what this means. But again, equal infinity is kind of a weird, it's not necessarily a mathematical expression. Equation can't equal infinity. So if you see what I'm saying, it's not like an equation definition. It's just an intuitive definition. But like looking at an example, like as I get closer and closer to a, I notice that it says that it doesn't necessarily even have to be defined at a, which is kind of like with the primary example 1 over x, right? 1 over x was undefined when x equals 0 because you can't divide by 0. But you could still look at what's happening as it gets closer and closer to 0. So even though the function may be undefined, you can still figure out the limit and see, well, is this limit actually defined? And looking at this particular graph, we see that, well, as we're approaching a from the right-hand side, and often this is, by definition, what we call a vertical asymptote. But in this particular graph, we see this is the location x is equal to a, and as we're getting closer and closer to that value, it appears as though the graph is going up towards infinity, or unlimited. Though again, we might not, you might wonder, well, how do I know it's not going to do that, or it's not going to have a little hump on it? It depends on the category of functions, and we might not be sure just by looking at the graph, which is, again, as I said before, why graphical limits, it's not the most precise way, but you can often figure it out just by guessing. Same with numerical, it's not always precise. Those are the main issues, but it's often easy to figure out, or quick. You can kind of determine that behavior fast. And also, from the left-hand side, it's the same thing. And just as I said in the last video, both directions are headed towards infinity. If both directions are going upward towards infinity, then that we would say that limit is equal to infinity and it checks out. If they're going in different directions, that we would say that limit is not infinity because both directions have to be the same in order for that limit to be said to exist. And very similarly, we say that if in both directions it's headed downwards on both the left and the right-hand side of the value of the function, we would say that limit is headed towards minus infinity or arbitrarily small. Let's look at an example. So let's see if we were to figure out what's the limit as x approaches 2 of 1 divided by x squared minus 4x plus 4. And again, we have a graph over here. You could always create a graph using a graphing calculator by going into your y equals menu and typing this in. We'll do this in an example here soon. But you should get a graph that looks something like this. And again, specifically, we could focus on the area around x is equal to 2 because that's kind of what we care about based on this limit. We want to know what's happening around the region of 2. So notice how this graph is has 2 as the focal point in the center, and we're kind of expanding it out to see, well, what's happening nearby. And based on the graph, notice how at 2, it appears as though the function has this break, this discontinuity, or it's not here. So if we were trying to figure out, well, what is f of 2, if we're trying to use that methodology, again, you could think about it as what we call direct substitution. What happens if I just plug in 2? Well, that would give me 1 divided by 4 minus 8 plus 4. And if I were to just plug in 2, well, 4 minus 8 is negative 4 plus 4. Notice what I end up here getting is 1 divided by 0, something which is undefined. So technically, 2 itself is undefined in this curve, and that's often why I might care about the limit at that specific location. So notice that this trick of finding a limit may work sometimes, as I said before, but that direct substitution doesn't always work. And that's when you want to try a different approach like, say, for example, a numerical or graphical approach. Now, looking at the graph, it's quite clear that on the left-hand side, it's going up to infinity, and on the right-hand side, it's also going up to infinity. And that's a very common behavior when you have undefined values, such as dividing by 0. And it's not uncommon to get an infinite limit. So the left-hand limit we'd say is infinity because there is no limit to it. It will become as large as you want. And the right-hand limit would also be headed towards infinity as well. And since those are both in agreement, again, when both the left and the right-hand side have the same limit, we'd say that the general limit is infinity as well. Now, trying to do all this on a calculator, let me grab where's my calculator at? Can't find it. Should have a calculator. Oh, there we go. Somewhere around here. I wanted to show you kind of how, like, if you didn't have a graph already created, you could always go into y equals. And in this menu, this will graph mathematical functions. If you wanted to graph a function such as 1 divided by x squared minus 4x plus 4, make sure that you use parentheses, or technically you can actually create fraction bar. If you go into, I believe it's alpha f1, you can actually make fractions like this and type it in like so, if you wanted to, but not all calculators have the ability to create fractions like this. So another way that you could do it with a graphing calculator is just type in 1 divided by parenthesis. And since, remember, the fraction bar is a grouping symbol which groups the top and the bottom separately, there's always an implied parentheses around functions. And if you're not really sure if you need to type in a parentheses or not, I would recommend that you just use parentheses just in case. But this would be the way I would type it in most simply. But we could always recreate a graph like this and kind of look at, well, what's happening around too. But another feature of having a graphing calculator is what's called the trace feature. If you hit this button right up here, it's kind of small, hopefully you can see it, but right near F4, trace will allow you to actually move your cursor along the function to any point that you want. And if I wanted to do it numerically, remember the idea of a numerical limit is I want to check in values that are very, very close by to, like 1.9 or 1.8, like from the left or from the right. So let's say I wanted to know, well, what's the left-handed limit, and I wanted to check it numerically. You can use a graphing calculator to do that. Let's just say I type in 1.9 now. If you're in the trace option and you just type in a value for x and hit enter, it will actually take you to the point on that curve and evaluate the value, what happens if I plug in 1.9. And if I plug in 1.9, what it gives me is y is equal to 100. And it might be kind of hard to determine, well, what is 100? What relevance does that have? But all that means is you get a fairly big number. And what happens if I get closer and closer to 2? That's kind of that's the question that the limit is asking. What happens as it approaches 2 from the left? Well, I get 100. Well, what if I get a little closer? What if I try 1.99? And that's kind of what I'd recommend, is try getting closer and closer, seeing what happens. Now, if I plug in 1.99, I get 10,000. What if I plug in 1.999? I get 1 million. And what I could see is that this is going to become infinitely large. And that's what the graph is kind of reflecting in this sort of weird position where it kind of seems to explode vertically upwards. But it's heading towards infinity. It is unrestrictedly large as I get closer and closer to 2. And if I check from the right-hand side, say, for example, 2.1, 2.11, or sorry, not 2.1, 2.01, or 2.00001, as I get sufficiently close to 2, it's getting really, really stinking big, unrestricted, in fact. And again, that's the whole idea for what this means, having an infinite limit.